Let's see, so the first one that someone asked about, okay, what mass of phosphorus is present in 25 grams? Oh wait, that's number 2. Number 3. A certain HCl solution is 30% HCl and has a density of 1.2 grams per milliliter. What mass of HCl is present in 167 mils of the solution? Okay, so for something like this, if you're having trouble kind of figuring out what all you have, so just kind of mark what you're given. We're given 167 mils of solution. We want the mass of HCl, not the mass of solution. And then as far as conversions go, this percentage is a conversion factor. There's 30, depending on what you want, 30 grams of HCl per 100 grams of solution. If you need a volume, you can do 30 mils of HCl per 100 mils of solution. Okay, we have that conversion factor. Also, the density is a conversion factor. And this is the solution density. Okay, so let's start with what we're given and try to convert it to what we want. So we'll write out 167 mils of solution. Okay, from there we can use this solution density to convert that to the grams of solution. So if you were to weigh 1.2 grams of solution, or if you were to weigh 1 mil of solution, the mass would be 1.2 grams. So that's the solution density. Okay, we can cross that out. Okay, now we have grams of solution. So using this percent conversion, we can convert to the grams of HCl. Okay, we cross out grams of solution, and we're left with grams of HCl. So you multiply that out. We're limited here and here to 2 sig figs, so you should get 60. Okay, any questions on this one? Yes? Number 12. All right, number 4. So it asks, which of the following statements is true? So this is just kind of trying to find out if you understand sort of the subatomic particles in an atom or an ion. So we'll go through each of these and prove them to be either true or false. So 73 Astatine -3 has 3 electrons. Okay. So look on the periodic table and find element AS. Its atomic number is 33. Okay, that tells us that regardless of what ion it is, it has 33 protons. Okay, now if it's neutral, it'll have the same number of electrons. Okay, but you're given AS -3. So that essentially has 3 more negative particles. Okay, and one thing to keep in mind, you can never, ever change the proton count. Okay, it has to stay 33. So in order to get a negative 33 charge, I'm going to add 3 electrons. So in reality, AS -3 has 36 electrons, not 3. So A is not true. Okay, let's look at 90Y plus 3. Okay, so find that on the periodic table. Okay, find Y is atomic number 39. That means it has 39 protons. Always. Doesn't matter if it's an ion or not. It doesn't matter if it has a charge. It always has 39 protons. So for this one, B has to be true. Okay, but let's just run through the other ones. So it says 41 potassium plus has 20 electrons. Okay, so potassium, atomic number 19. So it has 19 protons. If it's neutral, it'll have 19 electrons. Okay, but it's potassium plus. Well, K plus, you can't change the number of protons. Okay, but in order to get a positive 1 net charge, we need to lose 1 electron. So it'll have 18 electrons. So basically say 19 minus 18 is plus 1. That's how we get potassium plus. So that C is definitely not true with 20. 39 potassium has 39 neutrons. Well, 39 is the mass number. And that is the number of protons plus the number of neutrons. Well, potassium always has 19 protons. And the mass number is 39. So solve for the number of neutrons. And 39 potassium only has 20 neutrons. So D is not right. And then it says 40 argon has 18 neutrons. Argon is atomic number 18. So we do 40, 18 protons, plus the number of neutrons, so that should actually be 22. So E isn't correct either. So B is the only correct answer there. Okay? Yes?
Can you do 13?
Number 13. Okay, so how many atoms of boron are present in 0.2 moles of B2H6? Okay, when you're doing moles to atoms or moles to molecule conversion, you need Avogadro's number. That's 6.022 times 10 to the 23rd. You are given this number on the exam, so that's on the front page. So let's start with our 0.200 and write everything you have. Moles B2H6. Now, a common mistake is to go ahead and multiply this by Avogadro's number. But all that would give you is the number of B2H6 molecules. Okay, so we need to narrow this down just to boron. And the way we can read this chemical formula B2H6 is that in 1 mole of B2H6, there are 2 moles of boron, hence the B2. So we can cross out the B2H6. Now we have the moles of boron, but we want the atoms. There's 6.022 times 10 to the 23rd anything in a mole. So if we want atoms in a mole, we'll just write atoms. And we're left with the atoms of boron, which is, let's see, I have to calculate this one. 0.2 times 2 times 6.022 e to the 23rd. We have 3 sig figs, so I get 2.41 times 10 to the 23rd boron atoms. Yes?
So I'm a little confused about the difference between like coefficients and subscripts for moles, because in class today, when we were doing the example, 3O2 was written, and then that was 3 moles of oxygen, when instead of like 6.
Yeah, so let's try to talk through that. Okay, so let's walk through that one. It's a little bit of a tricky one. So the best way to do these is by doing the calculations, especially when it involves multiple steps. So it wants to know which of the following, they're all measured numbers, and which one contains 2 significant figures in the answer. Okay, so for A, it's a multiplication problem. Well, 0.05, that has 1 sig fig times something with 4 sig figs. So multiplication, you just take the one that has the smallest number. So your answer should only have 1 sig fig. So that one's not 2. Okay, now for B, addition and subtraction, it's really best to line your numbers up to figure it out. So let's work through B. We have 9.7 plus 0.3. Okay, draw your cutoff line Basically, it's your unit that contains the least number of digits past the decimal. So now if we add these up, you get 10.0. So your answer to this addition problem actually has 3 sig figs. That's the number of digits to the left of the red line. So B has 3 sig figs. Okay, let's try C. First, let's do the addition part. 1.6 plus 0.4. We get 2.0. There's our cutoff. This number only has 2 sig figs. So now let's do the division part of C. 1.6 divided by 2.0. It's a division problem. Each number contains 2 sig figs, so the answer should contain 2. So that's 1.6 divided by 2.0. You get 0.8, and it needs to have 2 sig figs, so 0.80. So 2, 2, and 2. So C does have 2 sig figs. Okay, and then for D, let's go ahead and walk through that one. For the addition part, we have 0.69 plus 0.2. Okay, there's our sig fig cutoff line. Get 0.89. That only has 1 sig fig in it. And I would just round that to 0.9. So for D, you have 0.69, which has 2 sig figs. The addition problem, which has 1, you're dividing, so the answer would only have 1 sig fig. So C is the only one that has 2 sig figs in the answer. Okay, does that make sense? All right. Any questions on this problem? All right. Other problems? Yes. Oh, do what? 10. Okay. All right, so this one takes several steps to get through the conversion, but if you're careful and systematic about it, it's not too hard. The other thing to be aware of is you did need to use some of the conversions on the front page of the exam. So what we want to start with here is our given, and we're given a surface area of 60 meters squared per gram. Whoops. Okay, and what I actually want to eventually get this to is we want units of yard square per pound. Okay, so when doing this type of conversion, either convert your numerator first or your denominator first, followed by the other. Okay, so the numerator is the hardest conversion here, so let's do that one first and get meters squared to yards squared. Okay, so the conversions we're going to need, which you can get from the front page of the exam, a yard is 36 inches. An inch is 2.54 centimeters. And the centimeter to meter conversion, I don't know if you were given that one. But that one, I think everybody knows that there's 100 centimeters in a meter. Okay, so using those conversions, we can get from meter squared to yard squared. So first, let's go from meter squared to centimeter squared, because that's the conversion we have. So I want to get rid of meters. So I'm going to put meter on the bottom, centimeter on the top. That's our conversion, but it's not just basic meters to centimeters, it's squared. So when it's squared, we have to square the number and the unit. So it's 100 square centimeter squared over 1 squared meter squared. Okay, that gets us out of meter squared units to centimeters. Now let's use the inch to centimeter conversion and do that one. So we can get rid of centimeters by putting it on the bottom. And again, we don't want just basic centimeters to inches, we want squared. So we'll square our units. As well as the numbers. Now we can cancel centimeter squared. We have units of inches squared, but we don't want that on top. We actually want yards squared. So we need one more conversion for the numerator. So write the conversion, 1 yard over 36 inches. And then square your units and your numbers. Okay, so now we have the top where we want it in yard square, but the denominator is still in grams. So we need to get that into pounds. And on the front page of the exam, you'll find the conversion. $453.59 grams is equal to 1 pound. So let's use this one. Okay, we want pounds at the bottom of our final number. So put that on the denominator of your conversion. We want to get rid of grams. Since right now it's on the bottom, we want to put that on the top. Now we can cancel out grams, and the units that we're left with, yards square on the top, pounds on the bottom. So multiply that out. It's easiest just to use the square button on your calculator for all of these squared numbers. But if you plug that into your calculator, you should end up with, let me just do it to get an actual number. Okay, I get a large number like 32549.3. Okay, but we're actually limited, and I should have had my decimal here. On the 60 that we start with, that's 2 sig figs, so our answer needs to have 2 sig figs. So we need to convert this to scientific notation. I'll round that to 3.3 times 10 to the 5th, and the units, yard square per pound. And I can't count. Oops, that's a big eraser. 3.3 times 10 to the fourth. Because we move our decimal point 1, 2, 3, 4 places. So then that gives us A is the correct answer. Yes?
Why don't you square the 60?
So you don't, the number you start with is essentially already squared, because if you say 60 meters squared, that's just saying it's 60 square meters. So you never square your starting number, just square your conversions. Yes?
Can you do number 11?
Okay, number 11. Okay, so you're given gunmetal, a mixture of copper, tin, zinc, and lead, contains 85% copper by weight. What mass of copper is present in 950 grams of gunmetal? Okay, so this is a percent conversion. And the way you want to essentially read this 85% copper by weight is saying, if you want to deal with grams, you can say that there are 85 grams of copper present in 100 grams of gunmetal. That's our whole. Okay, and that will allow us to have a conversion factor as well. Okay, now depending on what units you need, you could have written this as 85 kilograms of copper per 100 kilograms of gunmetal, 85 pounds of copper per 100 pounds of gunmetal, whatever unit you need there, because it's just part out of the whole. So again, this is just a conversion problem, so we'll start with what we're given. We have 950 grams of gunmetal. Okay, now we can use our percent factor as a conversion factor. So there's 85 grams of copper present in every 100 grams of gunmetal. The 100 part is taken to be exact, the 85 is measured. Okay, from there, though, the question wants the answer in kilograms of copper, not grams. So we need one more conversion. We want kilograms on top. For every 1 kilogram, that is equivalent to 1,000 grams. And that's an exact conversion there. So what we're left with is kilograms of copper once you multiply that out. So you should get 0.81 kilograms of copper, and the 85 is two significant figures, so we should have 2 in the answer. So we'll pick D. Okay, other questions? Yes? Number 3. Okay, so 12 is involving a temperature conversion. It asks, at what temperature do the Celsius and Fahrenheit scales read the same temperature? And I believe there is only one temperature where they do match. But in the absence of actually knowing this, you need to do the conversion. And you could use either conversion. Let's just use do temperature Fahrenheit is temperature Celsius times 1.8 plus 32. So basically, we're going to treat each of these as Celsius and convert them to Fahrenheit. You could have treated them all as Fahrenheit and converted to Celsius. See what matched. Okay, so what we want to do is plug in each of these numbers. Okay, so if you plug in 40 degrees for the temperature Celsius, you do 40 times 1.8 plus 32, you actually get a Fahrenheit temperature of 104. So that doesn't match. Okay, so then try plugging in B, which is negative 40. So we do negative 40 times 1.8 plus 32. You actually get negative 40 back out of that. So negative 40 degrees Celsius is actually the same, reads the same temperature as negative 40 Fahrenheit. You could plug in the other numbers. Do 11.4 Celsius. You get 52.5 Fahrenheit. Negative 11.4 Celsius. You get positive 11.5 Fahrenheit. So none of the other ones match. Yes?
On the exam, when we're balancing formulas, you want us to put 1 as a coefficient?
So the question is on the exam, balancing formulas, do I want you to put 1 as a coefficient? Okay, so 19, for example. All right, so this wants the molar mass of borax. So this you're going to use the number of atoms and the masses on the periodic table. So what we want to do here, let's just take this step by step and carefully. Okay, we'll start with the sodium. There's 2 of those. So we do 2 times, and the molar mass of sodium from the periodic table, 22.99. Okay, next, let's do the boron. There's 4 boron atoms. Its molar mass is 10.82. Okay, next let's just deal with this oxygen. So there's 7 oxygen there times a molar mass of 16. Okay, and in this case, the water is part of the formula as well. This dot just means that the water is sort of hydrated around the formula unit, but we still count that with the molar mass. So for the hydrogen, we do have to take account of this coefficient. So there's 10 times 2, there's 20 hydrogen in the water portion. You get we'll do 1.01. And then we have the oxygen from the water. And there's 10, since 10 is the coefficient that tells us there's 10 oxygen. Ten times 16. So now multiply all of these out. So 2, we get 45.98. 43.28. 112. 20.2. 160. So then we just add all of these up. I get 381. I'll cut my decimal off after one place. 381 point. My calculator I actually have 46, so this would round 381.5. I think B is the correct answer. I would say the difference that got it off just a little bit is probably use 15.99 for the molar mass of oxygen. That's why it got just a little higher. But that was certainly the closest one. Okay? All right, so we will stop there. I'll stick around for a few more minutes if anybody else wants to come up with a few final questions. So good luck on the exam tomorrow. That we're going to walk through is just how to use the different abundances of atomic mass to figure out what the atomic mass of some naturally occurring molecule is. So for this one, you're told that it's an unknown element, and it contains 3 different isotopes. And these isotopes are found to have the following masses: 38.9637, 39.9640, and 40.9618. Okay. Also, the relative abundance in nature is listed. So we have this first one about 93%, the second one well less than 1%, and the third one close to 7% abundance. So to get the average atomic mass, what we do is we take a weighted average of all of the isotopes. Okay, so the way we do the weighted average is remember that percent well, that's strange. Oh, nothing works. Okay, let's try now. So percent is really the part over the whole. Or the part over 100 is the way we typically do that. So that's how we're going to get the weighted parts out of these percentages. Okay, so let's start with each one, and we'll do 38.9637. Now, we want to figure out how much of that mass is contributed by the naturally occurring isotope, and it's going to be 93.08. So let's multiply this by 93.08 out of 100. Okay, so that'll get the weighted percentage or the weighted fraction of that isotope. And we're going to need to do this for each isotope and add them up. So the second isotope, 39.9640. And we multiply that by 0.012 out of 100. And then our third isotope, 40.9618. Times 6.91 out of 100. Okay, so if you multiply each of these out and add them up, then what you should get is 39.10. And we're just dealing with atomic mass units, so I'll say AMU. Okay, so you're given this list of different elements, so go through and compare what's on the periodic table, because those are the average atomic masses with this number. Okay, and you'll find the one that matches is potassium, 39.10. So the correct answer on that one is D. Okay, there will be a problem similar to this, so make sure you know how to do that. All right, any questions on this one? All right, so are there other specific problems you would like me to go through? Yes?
Number 9 says result in dealing with two significant figures, and all the equations, it should be two significant figures.
All right, so 19 is a balancing question. Okay, we want to go through and balance this one. So when doing the balancing, find your most complicated species. This is a combustion-like reaction. We're reacting with O2, but we produce sulfur trioxide as well. So let's start with our most complicated thing, and that's C4H8S2, and go ahead and stick a 1 in front of that. Okay, so this tells me here on the left, there's 4 carbons, 8 hydrogen, and 2 sulfur. Okay, so if we balance these, let's just start at CO2. I have 4 carbons on the left, I want 4 on the right. So we'll throw a 4 in front of that one. Okay, for water, that's my hydrogen on the right. Well, I have 8 on the left, I need 8 on the right, so let's put a 4 in front of the water. Okay, and then the sulfur, I have 2 on the left. So I want 2 on the right, so we'll put a 2 in front of SO3. So the tricky part here is just adding up all of your oxygens. So in the CO2, I have 4 times 2 is 8 oxygen. In the water, I have 4 times 1, that's 4. And the SO3, I have 2 times 3 is 6 oxygen. So that is 18 oxygen. Okay, so if there's 18 on the right, I need 18 on the left, so we'll put a 9 in front of the O2. So that's 9 times 2, that's my 18. So the equation's balanced. Now it just wants, for the answer, the sum of the coefficients. So we'll do 1 plus 9 plus 4 plus 4 plus 2. And that's 20. So easy answer there. Okay? Do you have a question? Number 4? Okay. If I can add a page here. Okay, so the question is kind of the difference in using moles for coefficients versus subscripts. And kind of the simplified answer is you can use it for whatever you need to. And it depends on kind of what you're reading. So let's do just a simple combustion reaction. Do C5H12 plus oxygen gives CO2 and water. Let's see if we can balance this easily. So I'll put a 1 there, a 5, a 6, and then for the oxygens, let's see, we have 10 oxygen, 6 oxygen, so we need 16 over here, so an 8. All right, so that one was pretty easy to balance. Now, as far as talking about the moles of something, we can read this equation in some different ways. So I could actually say, depending on the scale we're working on, oh, I'm sorry, not the atom. One single molecule of C5H12 reacts with 8 molecules of O2. Okay, now we typically don't work with single molecules, so we don't say those type of things a lot. We typically work on a mole scale. So another way to say this is if we have 1 mole of C5H12 reacts with 8 moles of O2. And when I'm saying a mole, I'm actually saying in a mole of C5H12, I'm saying that there are 6.022 times 10 to the 23rd molecules reacting with 8 times 6.022 times 10 to the 23rd molecules. Okay, so then I think your confusion, though, is coming where we used moles with the subscripts. So in these cases, we're talking about these as single units. But I can also say I can say 1 mole of C5H12 has 5 moles of carbon in it. Okay, because for the same way we could say a molecule of C5H12 has 5 carbon atoms in it. So it's just kind of the scale you're working on and how you want to talk about that. Does that help answer your question? Okay. Anything else on this? Okay, other problems? 19.